Hello everybody, Shanky here again. Today I'd like to talk about some of the flat earth proofs dealing with airplanes. Now I'm basing this information off of my 30 years as a commercial pilot. I will try not to get too technical because non-pilots sometimes don't understand all the aviation terms. If there's anything that I explain in this video that you don't understand, please leave it in the comments and I will try to answer your questions. Things that we'll talk about in this video are: do planes dip their nose to fly the curvature? Do plane routes prove anything? And do gyros prove anything? Now before I continue, I want to make it very clear. This video will not prove the earth is round. This video will not prove the earth is not flat. What this video will prove, or what I will show you, is that if the earth is round, that planes do not dip their nose to fly the curvature. This is a misconception that flat earthers have, and it should not be proof of anything. We'll also talk about plane routes, and are they proof of anything, and we'll talk about some gyros. The first thing we have to understand is the difference between straight and level. In this case, what I'll be discussing is level. It's different than being straight. As you can see in the diagram here, straight and level are two different things in aviation terms. Now let's talk about what is level, right? First of all, the earth as a circle, or the earth as a globe, obviously is round. A circle or a round object has a tangent line. At any point perpendicular to the radius of that circle is the tangent. That tangent is always perfectly level for the position it is in. I think we would all agree that this airplane would be level over the earth at this point. What about this airplane? Now, many people immediately say, well, yeah, it's going down. It looks like it's dipping the nose. Well, in fact, it is not, because as you can see, it is perfectly level for the tangent of the earth. So it is perfectly level for the position that it's in for the time. And in fact, this picture and the one you saw previously, this picture, are the exact same pictures. So if you agree that this one is level, this one is level as well. As you can see, as a plane continues around the earth, might be looked at like it is dipping its nose, but it's really not. As long as the plane stays level or parallel to the tangent line, it is level for the sphere that is over. But you have to remember, this, where the plane's nose is pointing at this particular time, this is not down. This is down. The plane is perfectly level for the position it's in at this time. I can use race cars as a good example. As race cars go around the track, they go around this curve. But look at each car. Each car, as it negotiates the curve, will stay perfectly level with the tangent line of the curve. At any time, if this car's nose points left of the tangent line, it will move out of place and basically it will run into the infield. It will lose its position around the curve. Now, the car's tires are pointed where the car is going, but the nose is just following, and the nose stays parallel to the tangent line. like an airplane, that you adjust the elevator and we adjust the flight controls to send the nose where we want it to go, but the nose is not pointing there. Another misconception, and this is why this is tricks a lot of flat earth people into not understanding this concept, is because of all the videos I've seen talking about the plane must dip their nose. It's because you show a giant plane over a small earth. Obviously, the scale is incorrect, and it's very, very misleading. Because as you see this giant plane going over the earth, and now it appears to be dipping its nose. Okay, fine. But in reality, is the plane this large over the earth? No. In reality, the plane is very, very small. As you can see the diagram here, this symbol, if it represents a plane, imagine this symbol is still hundreds and hundreds of times too large. And as it moves over the earth, as you can watch it, it is hundreds of times too large and hundreds of times too fast just in this simple diagram. But that's how an airplane would negotiate the earth. There's not that, the scale is incredibly small for the plane to negotiate the earth. But how small is it? Well, first let's talk about how planes fly. How does a pilot maintain that position? There's three flight controls, or there's three flight instruments that we must understand before we continue. The first is the attitude indicator. Okay, and the attitude indicator, an aviation term, do not confuse this with the attitude as a frame of mind, but the attitude meaning it is the position of the aircraft at a particular time. If the nose is pointing up, you could say that this is in nose high attitude. Just an aviation term. So the attitude indicator here, this one obviously showing wings level. We have the altimeter that shows our altitude, and our vertical speed, which shows an instantaneous climb or descent based on the altitude we're at. Now here's what is important to understand. This instrument, the altimeter, is 100% based on pressure. This instrument has no idea how high above the ground we are. In fact, often, most of the time, the pilot doesn't know how high above the ground we are, and he doesn't care. It is irrelevant. All we want to know is how high we are based on the pressure. The vertical speed indicator is also based on pressure, and it is an instantaneous indication if we are climbing or descending. If you look closely at this vertical speed indicator, it looks like we might be climbing at about 500 foot per minute. All right, so I'm climbing at not 500, I'm climbing at 50 feet per minute. If you look closely here, I'm climbing at about 50 feet. This would be 500 feet per minute. 50 feet per minute. A very small climb. It's really irrelevant. So if I wanted to adjust my climb, I would go back up here to my attitude indicator and I would say, the way I have this set right here looks level, but in fact, I've got a 50 foot per minute rated climb. I might nudge this down just a tiny bit. And I would want to level this out. And then I would fly a standard pressure. Now, what is the standard pressure? Or what I want to fly? It is important to note, like I mentioned before, that pilots don't know how high above the ground we are. Here's a simple approach plate for Centennial Airport in Denver, Colorado. We know that Denver is Mile High Stadium, It is roughly a mile above sea level. Well, that's also indicated here because as I'm doing this approach, my decision height, which is the lowest I can go on this approach, is 6,085 feet. That's on my altimeter. It is a pressure. This little symbol, this will tell me right here I'm 200 feet above the runway. Irrelevant. This is what I want to know, 600 or 6,085 feet. When I land, the airport elevation or the runway here, when I land on the runway, I'm at 5,885 feet. That is what my altimeter says. This is important to know, and I'll show you why in a minute. For an example, when I'm in Orlando, you see here, my approach might start at 9,000 feet, 8,000 on my descent down in Denver. Orlando, I'm at 5,000, 4,000, 3,200. My touchdown zone elevation, 94 feet. This is what it says on my altimeter. Altimeter doesn't know how high or even that I'm on the ground. All it knows is how high I am based on the pressure. Why is this important? Because if this is the Earth, and this is a standard pressure around the Earth at 30,000 feet, I would climb from a point, I would climb to this 30,000 feet, and I would maintain 30,000 feet. Here's some hills, high ground, low ground. We know that there's a lot of terrain around the Earth. The pilot doesn't care. When I get over a mountain at 30,000 feet, I might be 8, 10,000 feet above the ground at that point. Don't really care. When I'm over a low ground at 30,000 feet, or if I'm over the ocean, I'm 30,000 feet above the ocean. It doesn't matter. I just want to maintain that pressure. The pressure is what's important. And how I do that is I look at my altimeter here. I have it set at 30,000 feet. And when I get to 30,000 feet on my altimeter, I set the trims of the aircraft so my vertical speed is 0. If I have a small climb going, then my vertical speed will show a climb. My altimeter will subsequently show a small climb. Then I look at my attitude indicator, I readjust my wings level and make this back to 0, altimeter back to where I want it. Now here's something that most people cannot grasp. In an airplane, it is impossible for me to set the airplane to fly straight and level without knowing what my altitude is. I have to have a reference. Imagine if you were on a highway. You drive on a highway and you follow the white lines. You stay between the white lines. What if you were in the middle of a flat desert, completely flat, with no reference, no white lines to follow, and you were told to fly for 100 miles perfectly straight? You could hold your steering wheel perfectly straight, but I guarantee you, you would move inches, feet, hundreds of feet in one way or the other. You would never know without a reference. Well, this is the reference, our altitude. We set that on 30,000 feet and we maintain the 30,000 feet. Now, why do the passengers not feel this happening? Well, like I said before, the scale is very small. How small is the scale? Well, the Earth curves roughly 8 inches per mile. A typical airline here is a 737, it's about 110 feet. So that means for this airline, for the length of this plane, the Earth curves 0.15 inches. So as this plane makes one full run through the air, it has to account for 0.15 inches of curvature. And how much is that? It's about 2 pennies stacked. So if you want to say that the plane would dip its nose, then you would almost be technically correct, and it dips its nose to about 2 pennies from front to tail. That's it. Now I know what you're thinking right now. You're thinking, well, it's Shanky. It's not 8 inches a mile. It's 8 inches per mile squared. No, it's not. If you think it is, I will cover this at the end of the video if you want to stick around that long, and I'll explain to you why this is not the case. Now let's look at what this 0.15 degree of change on this airplane would be. All right, this is more of a modern glass cockpit look for an airplane, and you can see here is my attitude indicator. It looks like it might be slightly wings high, or slightly nose up, I should say. So it's slightly nose up, and if I wanted to adjust it by degree, it would look like this. This is a degree. Watch the yellow line. That is a degree of adjustment. This is 10 degrees up to here, 2.5, 5 degrees, 1 degree. Now, the curvature correction to adjust for 0.15 inches would be 0.01 degree of this. Another 0.01 degree of this. I can't even make the adjustment small enough where you can see it on this video. That is how small the adjustment would be. And again, how do I adjust this? I just make small corrections. I nudge this up and down until my vertical speed reads 0. I hope that was clear on planes and how you don't feel, or it's how it's not even necessary that they don't dip their nose going around the globe. If you have any questions, leave it in the comments, and we'll move on now to routes. Routes is a funny thing because I can see how this can also be misinterpreted. People say, wow, look, Shanky, I want to go from Australia to South America, but this route takes me through Europe. There must be some conspiracy. Well, no, there's not a conspiracy. What you have to remember is for legal and logistical reasons, airlines have hub airports. Frankfurt, for example, let's talk about Lufthansa. Lufthansa's hub is in Frankfurt, Germany. They don't have routes from Australia to South America. They have a route from Australia to Frankfurt, and they have a separate route from Frankfurt to South America. If you want to give Lufthansa your money, they would be happy to book you on Flight 1, Flight 2 to get you to your destination. But you're going to go through Frankfurt. That's just the way it is. The same thing for KLM in Amsterdam, British Airways in London, Turkish Airlines in Istanbul. These are all these hubs throughout Europe. If you look at the Lufthansa flight map, this is what it looks like. I can take any one of these segments to get to any one of these segments. It's just the way it works. I can't go from Australia to Dallas on Lufthansa. It's not a conspiracy. It's just they're separate routes. It is many different segments that they will get you to your destination on, through Frankfurt, obviously. But does that prove anything? Because if we look at the Qantas flight route or flight map, they do have a hub in Australia. So all their segments depart or originate in Australia, return to Australia. And look at that. South America, or I'm sorry, South Africa, South America, all these different places they can make it to. Direct flights. Now, are these flights legitimate? Yeah, of course they are. Thousands and thousands of people take these flights every month. Thousands a month are on these flights out of here, right? In fact, you can track these flights. If these flights were not legitimate from Australia to South America, for example, I think you would see yourself going over northern or Washington, northern eastern United or western United States. Same thing with Australia to Johannesburg, through China, through Russia, over the middle of Saudi Arabia. No, that's not the way the flight route goes. So it's just impossible for these routes to fly on this flight map the way it shows. But I did pull up the flight from Sydney to San Diego, and I tracked it. And this is a screenshot of when it was halfway there. Flight was shown that is halfway to San Diego. Yes, it's making a curved line. That's because we fly a great circle track. This is when you take a globe and you flatten it out, the route is going to appear to be curved. No big deal. You can play around with this, and I'm going to encourage you to do so. Go to this website right here. There's a few websites that will do this. This is one of the better ones, I think. And you can type in any lat long from point 1, point 2 in the world, and it will draw a great circle track. You use this great circle track to determine the shortest distance. Also on this website, it has a place where you can put the rhumb line and or put the same lat longs to determine a rhumb line distance. Play around with it a little bit and see the difference and see what great circles really mean. One thing that's I thought interesting, you put in the lat long from Sydney to Santiago. It gives you a midpoint. I looked at the midpoint and I plotted it on Google Earth. And I ended up with the midpoint here between Sydney and Santiago. This is the midpoint. Now, going back one, I want to point out that the math involved in this can be quite complicated. I won't deny that. It's spherical trigonometry. It deals with sines and cosines. It can be done. It's not impossible, but it is a bit complicated. A mathematical problem being complicated should not be proof that it doesn't exist, because we use this all the time. In fact, I have seen programs where you type in the problem and it will give you the answer. It is not hard to do. It's called the Haversine formula. You can look it up. So we'd like to talk now about gyros and how they work. Yes, I know. You take off, your gyro's spinning, and how does it compensate for the curvature? Well, because it does. Because inside an aircraft is not a perfect gyro. The gyro in an aircraft is in an enclosed capsule. It's enclosed using air pressure to turn the gyro and these vents at the bottom called pendulous vanes. The pendulous vane is basically an opening, 4 sides on the opening, that will vent air and erect the gyro as necessary. This because these slats will always point towards the ground. I'm going to say gravity. You're going to freak out if you don't believe gravity is real. Call it density. But it just, because that's the way it works. They will always point to the ground, so as the gyro tilts, these will slide off the hole and vent the air. And the venting air self-erects the gyro. Here's a picture of one on an actual gyro. As the gyro is tilted, you can see the slat has fallen open and it is allowed air to vent out of the pendulous veins right here. Here is a challenge. If you don't believe that this is actually the way they work, or this is not the design, think about this. In any aircraft owner's manual, is there a place in the operator's manual that says before you start the aircraft, make sure you're on complete, straight, and level ground? There's not one. We can start the aircraft on any type of a slope. Many airport, as you can see this one, it may be, many airports design their parking areas with a slight slope for drainage. It lets the water run off. Now, if the ground was sloped when I started my aircraft and I first put power to my gyro, wouldn't the gyro maintain the position that it's in on that slope? How does it know to go to zero at that point or to level? The only reason it knows is it has a self-erecting mechanism. All right, hope I cleared that up. That was everything about, do airplanes need to dip the nose, flight routes explained, and gyros. Now, if you want to stick with me, we're going to talk about, does the Earth curve at 8 inches a mile or 8 inches a mile squared? Okay, let's just assume, first we have to, if the Earth is round, we're talking about the round Earth, at no point does a circle, because we're talking about the round Earth being a circle, at no point does it curve or does it arc. Arc is a better term. At no point does it arc any more than it does at any other point. That's what makes it a circle. If it didn't, it would be a spiral. From here, this segment, this segment, this segment, it doesn't matter. It's a freaking arc. It's the same arc all the way around. Looking at this, would you agree this is a circle? Yeah, most people would agree this is a circle. Actually, this is an oblate spheroid. And this oblate spheroid is drawn to the same dimensions as the Earth. That is 0.04% wider at the equator. So yeah, it looks round. It's actually not completely round. It's an oblate spheroid. Should that make that much difference? No, it makes no difference. The 0.00, such a small difference in the arc over the equator than it would be on the outer parts. Sorry. Yeah, so like I said, if the Earth curved exponentially more as you moved, it would be a spiral. Nobody ever said the Earth is a spiral. But let me back up and say, well, okay, Shanky, what is 8 inches a mile squared? Yes, 8 inches a mile squared is the visual distance from an observer to the horizon. This is for an observer that is not moving, the visual distance to observer to the horizon, right? That's what that is. And there's a reason for that, because I have to look over the first mile, and I have to look over the second mile, and I have to look over a third mile. That's exponential. If I was moving, I'm always looking over the first mile. So if you want to think about it like this, it is 8 inches per mile squared, but that formula is being updated every time, instantaneously, every time I move, everywhere you move. If that's not the case, we're not sitting here where we grew up, probably, or we're not sitting where we were born. We have moved, right? Has the earth exponentially, or would the earth exponentially curve more? Is it based on time? If I took off from New York and I flew to Los Angeles, what would be the earth's curvature when I got to Los Angeles? Would I get off the plane and it's exponentially more than 8 inches a mile? But wait, for everybody that lives in LA, it is 8 inches a mile for the first mile. So why would it be any different for me? It's not. The curvature is 8 inches a mile. The visual distance to the horizon is what is 8 inches per mile squared.